Quantum computing. Quantum computing is the use of quantum mechanical phenomena such as superposition and entanglement to perform computation. A quantum computer is used to perform such computation, which can be implemented theoretically or physically. I-5 The field of quantum computing is actually a subfield of quantum information science, which includes quantum cryptography and quantum communication. Quantum computing was started in the early 1980s when Richard Feynman and Yuri Manin expressed the idea that a quantum computer had the potential to simulate things that a classical computer could not. In 1994, Peter Shor shocked the world with an algorithm that had the potential to decrypt all secured communications. There are two main approaches to physically implementing a quantum computer currently: analog and digital. Analog approaches are further divided into quantum simulation, quantum annealing, and adiabatic quantum computation. Digital quantum computers use quantum logic gates to do computation. Both approaches use quantum bits or qubits 2-13. Qubits are fundamental to quantum computing and are somewhat analogous to bits in a classical computer. Qubits can be in a 1 or 0 quantum state. But they can also be in a superposition of the 1 and 0 states. However, when qubits are measured, the result is always either a 0 or a 1. The probabilities of the two outcomes depends on the quantum state they were in. Today's physical quantum computers are very noisy, and quantum error correction is a burgeoning field of research. Unfortunately, existing hardware is so noisy that fault-tolerant quantum computing is still a rather distant dream. As of April 2019, neither large scalable quantum hardware has been demonstrated nor have commercially useful algorithms for today's small noisy quantum computers been published. There is an increasing amount of investment in quantum computing by governments, established companies, and startups. Both applications of near-term intermediate-scale devices and the demonstration of quantum supremacy are actively pursued in academic and industrial research. Contents. Basics. A classical computer has a memory made up of bits, where each bit is represented by either a 1 or a 0. A quantum computer, on the other hand, maintains a sequence of qubits, which can represent a 1, a 0, or any quantum superposition of those two qubit states. 13-16 A pair of qubits can be in any quantum superposition of 4 states, 16 and 3 qubits in any superposition of 8 states. In general, a quantum computer with n qubits can be in any superposition of up to 2 n different states, 17. This compares to a normal computer that can only be in one of these states at any one time. A quantum computer operates on its qubits using quantum gates and measurement, which also alters the observed state. An algorithm is composed of a fixed sequence of quantum logic gates, and a problem is encoded by setting the initial values of the qubits, similar to how a classical computer works. The calculation usually ends with a measurement, collapsing the system of qubits into one of the eigenstates, where each qubit is 0 or 1, decomposing into a classical state. The outcome can, therefore, be at most classical bits of information. If the algorithm did not end with a measurement, the result is an unobserved quantum state. Such unobserved states may be sent to other computers as part of distributed quantum algorithms. Quantum algorithms are often probabilistic, in that they provide the correct solution only with a certain known probability. Non-deterministic has a different meaning in computer science. An example of an implementation of qubits of a quantum computer could start with the use of particles with two spin states, down and up, typically written \down arrow \wrangle and \up \wrangle. Or 0 \wrangle and 1 \wrangle. This is true because any such system can be mapped onto an effective spin 1/2 system. Principles of operation. N. Operation. While a classical 3-bit state and a quantum 3-qubit state are each 8-dimensional vectors, they are manipulated quite differently for classical or quantum computation. For computing in either case, the system must be initialized, for example into the all zeros string, 000 \wrangle, corresponding to the vector 1,0,0,0,0,0,0,0,0,0. In classical randomized computation, the system evolves according to the application of stochastic matrices, which preserve that the probabilities add up to 1, i.e., preserve the L1 norm. In quantum computation, on the other hand, allowed operations are unitary matrices, which are effectively rotations. They preserve that the sum of the squares add up to 1, the Euclidean or L2 norm. Exactly what unitaries can be applied depend on the physics of the quantum device. Consequently, since rotations can be undone by rotating backward, quantum computations are reversible. Technically, quantum operations can be probabilistic combinations of unitaries, so quantum computation really does generalize classical computation. See quantum circuit for a more precise formulation. Finally, upon termination of the algorithm, the result needs to be read off. In the case of a classical computer, we sample from the probability distribution on the 3-bit register to obtain one definite 3-bit string, say 000. Quantum mechanically, 1 the 3-qubit state, which is equivalent to collapsing the quantum state down to a classical distribution, with the coefficients in the classical state being the squared magnitudes of the coefficients for the quantum state, as described above, followed by sampling from that distribution. This destroys the original quantum state. Many algorithms will only give the correct answer with a certain probability. However, by repeatedly initializing, running, and measuring the quantum computer's results, the probability of getting the correct answer can be increased. In contrast, counterfactual quantum computation allows the correct answer to be inferred when the quantum computer is not actually running in a technical sense, though earlier initialization and frequent measurements are part of the counterfactual computation protocol. Potential cryptography. Integer factorization, which underpins the security of public key cryptographic systems, is believed to be computationally infeasible with an ordinary computer for large integers if they are the product of few prime numbers, e.g., products of two 300-digit primes. By comparison, a quantum computer could efficiently solve this problem using Shor's algorithm to find its factors. This ability would allow a quantum computer to break many of the cryptographic systems in use today, in the sense that there would be a polynomial time, in the number of digits of the integer, algorithm for solving the problem. In particular, most of the popular public key ciphers are based on the difficulty of factoring integers or the discrete logarithm problem, both of which can be solved by Shor's algorithm. In particular, the RSA, Diffie-Hellman, and elliptic curve Diffie-Hellman algorithms could be broken. These are used to protect secure web pages, encrypted email, and many other types of data. Breaking these would have significant ramifications for electronic privacy and security. However, other cryptographic algorithms do not appear to be broken by those algorithms. Some public key algorithms are based on problems other than the integer factorization and discrete logarithm problems to which Shor's algorithm applies, like the Michelai crypto system based on a problem encoding theory. Lattice-based crypto systems are also not known to be broken by quantum computers, and finding a polynomial time algorithm for solving the dihedral hidden subgroup problem, which would break many lattice-based crypto systems, is a well-studied open problem. It has been proven that applying Grover's algorithm to break a symmetric, secret key algorithm by brute force requires time equal to roughly 2n/2 invocations of the underlying cryptographic algorithm, compared with roughly 2n in the classical case, meaning that symmetric key lengths are effectively halved. AES 256 would have the same security against an attack using Grover's algorithm that AES 128 has against classical brute force search. See key size. Quantum cryptography could potentially fulfill some of the functions of public key cryptography. Quantum-based cryptographic systems could, therefore, be more secure than traditional systems against quantum hacking. Quantum search. Besides factorization and discrete logarithms, quantum algorithms offering a more than polynomial speedup over the best-known classical algorithm have been found for several problems, including the simulation of quantum physical processes from chemistry and solid-state physics, the approximation of Jones polynomials, and solving Pell's equation. No mathematical proof has been found that shows that an equally fast classical algorithm cannot be discovered, although this is considered unlikely. However, quantum computers offer polynomial speedup for some problems. The most well-known example of this is quantum database search, which can be solved by Grover's algorithm using quadratically fewer queries to the database than that are required by classical algorithms. In this case, the advantage is not only provable but also optimal. It has been shown that Grover's algorithm gives the maximal possible probability of finding the desired element for any number of oracle lookups. Several other examples of provable quantum speedups for query problems have subsequently been discovered, such as for finding collisions in 2-to-1 functions and evaluating NAND trees. Problems that can be addressed with Grover's algorithm have the following properties. 1. There is no searchable structure in the collection of possible answers. 2. The number of possible answers to check is the same as the number of inputs to the algorithm, and 3. There exists a Boolean function which evaluates each input and determines whether it is the correct answer. For problems with all these properties, The running time of Grover's algorithm on a quantum computer will scale as the square root of the number of inputs, or elements in the database, as opposed to the linear scaling of classical algorithms. A general class of problems to which Grover's algorithm can be applied is Boolean satisfiability problem. In this instance, the database through which the algorithm is iterating is that of all possible answers. An example, and possible, application of this is a password cracker that attempts to guess the password or secret key for an encrypted file or system. Symmetric ciphers such as Tripleday and AES are particularly vulnerable to this kind of attack. This application of quantum computing is a major interest of government agencies. Quantum simulation. Since chemistry and nanotechnology rely on understanding quantum systems, and such systems are impossible to simulate in an efficient manner classically, many believe quantum simulation will be one of the most important applications of quantum computing. Quantum simulation could also be used to simulate the behavior of atoms and particles at unusual conditions such as the reactions inside a collider. Quantum annealing and adiabatic optimization. Adiabatic quantum computation relies on the adiabatic theorem to undertake calculations. A system is placed in the ground state for a simple Hamiltonian, which is slowly evolved to a more complicated Hamiltonian whose ground state represents the solution to the problem in question. The adiabatic theorem states that if the evolution is slow enough, the system will stay in its ground state at all times through the process. Solving linear equations. The quantum algorithm for linear systems of equations, or HHL algorithm, named after its discoverers Harrow, Hasidim, and Lloyd, is expected to provide speedup over classical counterparts. Quantum supremacy. John Preskill has introduced the term to refer to the hypothetical speedup advantage that a quantum computer would have over a classical computer in a certain field. Google announced in 2017 that it expected to achieve quantum supremacy by the end of the year, though that did not happen. IBM said in 2018 that the best classical computers will be beaten on some practical task within about 5 years and views the quantum supremacy test only as a potential future benchmark. Quantum supremacy has not been achieved yet, and skeptics like Gil Colley doubt that it will ever be. Bill Unruh doubted the practicality of quantum computers in a paper published back in 1994. Paul Davies argued that a 400-qubit computer would even come into conflict with the cosmological information bound implied by the holographic principle. Obstacles. There are a number of technical challenges in building a large-scale quantum computer, and thus far quantum computers have yet to solve a problem faster than a classical computer. David DiVincenzo, of IBM, listed the following requirements for a practical quantum computer. Scalable physically to increase the number of qubits. Qubits that can be initialized to arbitrary values. Quantum gates that are faster than decoherence time. Universal gate set. Qubits that can be read easily. Quantum decoherence. One of the greatest challenges is controlling or removing quantum decoherence. This usually means isolating the system from its environment as interactions with the external world cause the system to decohere. However, other sources of decoherence also exist. Examples include the quantum gates, and the lattice vibrations and background thermonuclear spin of the physical system used to implement the qubits. Decoherence is irreversible, as it is effectively non-unitary, and is usually something that should be highly controlled, if not avoided. Decoherence times for candidate systems, in particular, the transverse relaxation time T2, for NMR and MRI technology, also called the dephasing time, typically range between nanoseconds and seconds at low temperature. Currently, some quantum computers require their qubits to be cooled to 20 millikelvins in order to prevent significant decoherence. As a result, time-consuming tasks may render some quantum algorithms inoperable, as maintaining the state of qubits for a long enough duration will eventually corrupt the superpositions. These issues are more difficult for optical approaches as the time scales are orders of magnitude shorter, and an often cited approach to overcoming them is optical pulse shaping. Error rates are typically proportional to the ratio of operating time to decoherence time, hence any operation must be completed much more quickly than the decoherence time. As described in the quantum threshold theorem, if the error rate is small enough, it is thought to be possible to use quantum error correction to suppress errors and decoherence. This allows the total calculation time to be longer than the decoherence time if the error correction scheme can correct errors faster than decoherence introduces them. An often cited figure for the required error rate in each gate for fault-tolerant computation is 10^3, assuming the noise is depolarizing. Meeting this scalability condition is possible for a wide range of systems. However, The use of error correction brings with it the cost of a greatly increased number of required qubits. The number required to factor integers using Shor's algorithm is still polynomial, and thought to be between L and L2, where L is the number of qubits in the number to be factored. Error correction algorithms would inflate this figure by an additional factor of L. For a 1000-bit number, this implies a need for about 104 bits without error correction. With error correction, the figure would rise to about 107 bits. Computation time is about L2 or about 107 steps, and at 1 MHz, about 10 seconds. A very different approach to the stability decoherence problem is to create a topological quantum computer with anyons, quasi-particles used as threads and relying on braid theory to form stable logic gates. Developments: quantum computing models. There are a number of quantum computing models, distinguished by the basic elements in which the computation is decomposed. The four main models of practical importance are: quantum gate array, computation decomposed into a sequence of few-qubit quantum gates. One-way quantum computer, computation decomposed into a sequence of 1-qubit measurements applied to a highly entangled initial state or cluster state. Adiabatic quantum computer, based on quantum annealing, computation decomposed into a slow continuous transformation of an initial Hamiltonian into a final Hamiltonian, whose ground states contain the solution. Topological quantum computer, computation decomposed into the braiding of anyons in a 2D lattice. The quantum Turing machine is theoretically important, but the direct implementation of this model is not pursued. All four models of computation have been shown to be equivalent. Each can simulate the other with no more than polynomial overhead. Quantum physical realizations. For physically implementing a quantum computer, many different candidates are being pursued, among them, distinguished by the physical system used to realize the qubits. Trapped ion quantum computer, qubit implemented by the internal state of trapped ions. Optical lattices, qubit implemented by internal states of neutral atoms trapped in an optical lattice. Quantum dot computer, spin-based, e.g. the Lost of Vincenzo quantum computer, qubit given by the spin states of trapped electrons. Quantum dot computer, spatial-based, qubit given by electron position in double quantum dot. Coupled quantum wire, qubit implemented by a pair of quantum wires coupled by a quantum point contact. Nuclear magnetic resonance quantum computer, NMRQC, implemented with the nuclear magnetic resonance of molecules in solution, where qubits are provided by nuclear spins within the dissolved molecule and probed with radio waves. Solid-state NMR-Kane quantum computers, qubit realized by the nuclear spin state of phosphorus donors in silicon. Electrons on helium quantum computers, qubit is the electron spin. Cavity quantum electrodynamics, CQED, qubit provided by the internal state of trapped atoms coupled to -s cavities. Molecular magnet, qubit given by spin states. Fullerene-based ESR quantum computer, qubit based on the electronic spin of atoms or molecules encased in fullerenes. Linear optical quantum computer, qubits realized by processing states of different modes of light through linear elements, e.g. mirrors, beam splitters and phase shifters. Transistor-based quantum computer, string quantum computers with entrainment of positive holes using an electrostatic trap. Rare earth metal ion doped inorganic crystal-based quantum computers, qubit realized by the internal electronic state of dopants in optical fibers. Metallic-like carbon nanospheres-based quantum computers. A large number of candidates demonstrates that the topic, in spite of rapid progress, is still in its infancy. There is also a vast amount of flexibility. Timeline. In 1959, Richard Feynman, in his lecture, "There's Plenty of Room at the Bottom," states the possibility of using quantum effects for computation. In 1980, Paul Benioff described quantum mechanical Hamiltonian models of computers, and the Russian mathematician Yuri Manin motivated the development of quantum computers. In 1981, at a conference organized by MIT and IBM, physicist Richard Feynman urged the world to build a quantum computer. He said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy." In 1985, David Deutsch describes the first universal quantum computer. Just as a universal Turing machine can simulate any other Turing machine efficiently, Church-Turing thesis, so the universal quantum computer is able to simulate any other quantum computer with at most a polynomial slowdown. In 1992, David Deutsch and Richard Josse propose a computational problem that can be solved efficiently with the determinist Deutsch-Josse algorithm on a quantum computer, but for which no deterministic classical algorithm is possible. This was perhaps the earliest result in the computational complexity of quantum computers, proving that they were capable of performing some well-defined computational task more efficiently than any classical computer. In 1993, an international group of 6 scientists, including Charles Bennett, showed that perfect quantum teleportation is possible in principle, but only if the original is destroyed. In 1994, Peter Shor, at MIT's Bell Labs, discovered an important quantum algorithm, which allows a quantum computer to factor large integers exponentially much faster than the best-known classical algorithm. Shor's algorithm can theoretically break many of the public key cryptography systems in use today, sparking a tremendous interest in quantum computers. In 1996, the DiVincenzo's criteria are published, which are a list of conditions that are necessary for constructing a quantum computer, proposed by the theoretical physicist David P. DiVincenzo in his 2000 paper, The Physical Implementation of Quantum Computation. In 2001, researchers demonstrated Shor's algorithm to factor 15 using a 7-qubit NMR computer. In 2005, researchers at the University of Michigan built a semiconductor Shipian trap. Such devices from standard lithography may point the way to scalable quantum computing. In 2009, researchers at Yale University created the first solid-state quantum processor. The 2-qubit superconducting chip had artificial atom qubits made of a billion aluminum atoms that acted like a single atom that could occupy 2 states. A team at the University of Bristol also created a silicon chip based on quantum optics, able to run Shor's algorithm. Further developments were made in 2010. Springer publishes a journal, Quantum Information Processing, devoted to the subject. In February 2010, digital combinational circuits like an adder, subtractor etc. are designed with the help of symmetric functions organized from different quantum gates. In April 2011, a team of scientists from Australia and Japan made a breakthrough in quantum teleportation, successfully transferring a complex set of quantum data with full transmission integrity, without affecting the qubits' superpositions. In 2011, D-Wave Systems announced the first commercial quantum annealer, the D-Wave 1, claiming a 128-qubit processor. On May 25, 2011, Lockheed Martin agreed to purchase a D-Wave 1 system. Lockheed and the University of Southern California, USC, will house the D-Wave 1 at the newly formed USC Lockheed Martin Quantum Computing Center. D-Wave's engineers designed the chips with an empirical approach, focusing on solving particular problems. Investors liked this more than academics, who said D-Wave had not demonstrated that they really had a quantum computer. Criticism softened after a D-Wave paper in that proved that the chips have some quantum properties. 2 published papers have suggested that the D-Wave machine's operation can be explained classically, rather than requiring quantum models. Later work showed that classical models are insufficient when all available data is considered. Experts remain divided on the ultimate classification of the D-Wave systems, though their quantum behavior was established concretely with a demonstration of entanglement. During the same year, researchers at the University of Bristol created an all-bulk optics system that ran a version of Shor's algorithm to successfully factor 21. In September 2011, researchers proved quantum computers can be made with a von Neumann architecture, separation of RAM. In November 2011, researchers factorized 143 using 4 qubits. In February 2012, IBM scientists said that they had made several breakthroughs in quantum computing with superconducting integrated circuits. In April 2012, a multinational team of researchers from the University of Southern California, the Delft University of Technology, the Iowa State University of Science and Technology, and the University of California, Santa Barbara constructed a 2-qubit quantum computer on a doped diamond crystal that can easily be scaled up and is functional at room temperature. 2 logical qubit directions of electron spin and nitrogen kernels spin were used, with microwave impulses. This computer ran Grover's algorithm, generating the right answer on the first try in 95% of cases. In September 2012, Australian researchers at the University of New South Wales said the world's first quantum computer was just 5 to 10 years away, after announcing a global breakthrough enabling the manufacture of its memory building blocks. A research team led by Australian engineers created the first working qubit based on a single atom in silicon, invoking the same technological platform that forms the building blocks of modern-day computers. In October 2012, Nobel Prizes were awarded to David J. Wineland and Serge Haroche for their basic work on understanding the quantum world, which may help make quantum computing possible. In December 2012, 1QBIT, the first dedicated quantum computing software company, was founded in Vancouver, BC. 1QBIT is the first company to focus exclusively on commercializing software applications for commercially available quantum computers, including the D-Wave 2. 1QBIT's research demonstrated the ability of superconducting quantum annealing processors to solve real-world problems. In February 2013, a new technique, boson sampling, was reported by two groups using photons in an optical lattice that is not a universal quantum computer, but may be good enough for practical problems. In May 2013, Google announced that it was launching the Quantum Artificial Intelligence Lab, hosted by NASA's Ames Research Center, with a 512-qubit D-Wave quantum computer. The university's Space Research Association, USRA, will invite researchers to share time on it with the goal of studying quantum computing for machine learning. Google added that they had already developed some quantum machine learning algorithms and had learned some useful principles, such as that best results come from mixing quantum and classical computing. In early 2014, based on documents provided by former NSA contractor Edward Snowden, it was reported that the U.S. National Security Agency, NSA, is running a $79.7 million research program titled Penetrating Hard Targets, to develop a quantum computer capable of breaking vulnerable encryption. In 2014, a group of researchers from ETH Zurich, USC, Google, and Microsoft reported a definition of quantum speedup, and were not able to measure quantum speedup with the D-Wave 2 device, but did not explicitly rule it out. In 2014, researchers at University of New South Wales used silicon as a protectant shell around qubits, making them more accurate, increasing the length of time they will hold information, and possibly making quantum computers easier to build. In April 2015, IBM scientists claimed two critical advances towards the realization of a practical quantum computer, claiming the ability to detect and measure both kinds of quantum errors simultaneously, as well as a new, square quantum bit circuit design that could scale to larger dimensions. In October 2015, QTech successfully conducted the loophole-free Bell inequality violation test using electron spins separated by January 3 kilometers. In October 2015, researchers at the University of New South Wales built a quantum logic gate in silicon for the first time. In December 2015, NASA publicly displayed the world's first fully operational quantum-computer-made D-Wave systems at the Quantum Artificial Intelligence Lab at its Ames Research Center. The device was purchased in 2013 via a partnership with Google and University's Space Research Association. The presence and use of quantum effects in the D-Wave quantum processing unit is more widely accepted. In some tests, it can be shown that the D-Wave quantum annealing processor outperforms Selby's algorithm. Only two of these computers have been made so far. In May 2016, IBM Research announced that for the first time ever it is making quantum computing available to members of the public via the cloud, who can access and run experiments on IBM's quantum processor, calling the service the IBM Quantum Experience. The quantum processor is composed of 5 superconducting qubits and is housed at IBM's Thomas J. Watson Research Center. In August 2016, scientists at the University of Maryland successfully built the first reprogrammable quantum computer. In October 2016, the University of Basel described a variant of the electron hole-based quantum computer, which instead of manipulating electron spins, uses electron holes in a semiconductor at low, mK, temperatures, which are much less vulnerable to decoherence. This has been dubbed the positronic quantum computer, as the quasi-particle behaves as if it has a positive electrical charge. In March 2017, IBM announced an industry-first initiative, called IBM Q, to build commercially available universal quantum computing systems. The company also released a new API for the IBM Quantum Experience that enables developers and programmers to begin building interfaces between its existing 5-qubit cloud-based quantum computer and classical computers, without needing a deep background in quantum physics. In May 2017, IBM announced that it had successfully built and tested its most powerful universal quantum computing processors. The first is a 16-qubit processor that will allow for more complex experimentation than the previously available 5-qubit processor. The second is IBM's first prototype commercial processor with 17 qubits, and leverages significant materials, device, and architecture improvements to make it the most powerful quantum processor created to date by IBM. In July 2017, a group of U.S. researchers announced a quantum simulator with 51 qubits. The announcement was made by Mikhail Lukin of Harvard University at the International Conference on Quantum Technologies in Moscow. A quantum simulator differs from a computer. Lukin's simulator was designed to solve one equation. Solving a different equation would require building a new system, whereas a computer can solve many different equations. In September 2017, IBM research scientists used a 7-qubit device to model beryllium hydride molecule, the largest molecule to date by a quantum computer. The results were published as the cover story in the peer-reviewed journal Nature. In October 2017, IBM research scientists successfully broke the 49-qubit simulation barrier and simulated 49 and 56-qubit short-depth circuits, using the Lawrence Livermore National Laboratory's Vulkan supercomputer, and the University of Illinois' Cyclops tensor framework, originally developed at the University of California. In November 2017, the University of Sydney research team successfully made a microwave circulator, an important quantum computer part, that was 1,000 times smaller than a conventional circulator, by using topological insulators to slow down the speed of light in a material. In December 2017, IBM announced its first IBM Q network clients. The companies, universities, and labs that will explore practical business and science quantum applications, using IBM Q 20-qubit commercial systems, include J.P. Morgan Chase, Daimler AG, Samsung, JSR Corporation, Barclays, Hitachi Metals, Honda, Nagas, Keio University, Oak Ridge National Lab, Oxford University, and University of Melbourne. In December 2017, Microsoft released a preview version of a quantum development kit, which includes a programming language, Q number, that can be used to write programs that are run on an emulated quantum computer. In 2017, D-Wave was reported to be selling a 2,000-qubit quantum computer. In late 2017 and early 2018, IBM, Intel, and Google each reported testing quantum processors containing 50, 49, and 72 qubits, respectively, all realized using superconducting circuits. By number of qubits, these circuits are approaching the range in which simulating their quantum dynamics is expected to become prohibitive on classical computers, although it has been argued that further improvements in error rates are needed to put classical simulation out of reach. In February 2018, scientists reported, for the first time, the discovery of a new form of light, which may involve polaritons, that could be useful in the development of quantum computers. In February 2018, QTech reported successfully testing a silicon-based 2-spin qubits quantum processor. In June 2018, Intel began testing a silicon-based spin-qubit processor, manufactured in the company's D1D fab in Oregon. In July 2018, a team led by the University of Sydney achieved the world's first multi-qubit demonstration of a quantum chemistry calculation performed on a system of trapped ions, one of the leading hardware platforms in the race to develop a universal quantum computer. In December 2018, IonQ reported that its machine could be built as large as 160 qubits. In January 2019, IBM launched IBM Q System 1, its first integrated quantum computing system for commercial use. IBM Q System 1 is designed by industrial design company Map Project Office and interior design company Universal Design Studio. In March 2019, a group of Russian scientists used the open-access IBM quantum computer to demonstrate a protocol for the complex conjugation of the probability amplitudes needed for time reversal of a physical process, in this case, for an electron scattered on a 2-level impurity, a 2-qubit experiment. However, for the 3-qubit experiment, the amplitude fell below 50%, failure of time reversal, due to its increased complexity. Relation to computational complexity theory. The class of problems that can be efficiently solved by quantum computers is called BQP, for bounded error, quantum, polynomial time. Quantum computers only run probabilistic algorithms, so BQP on quantum computers is the counterpart of BPP, bounded error, probabilistic, polynomial time, on classical computers. It is defined as the set of problems solvable with a polynomial time algorithm, whose probability of error is bounded away from 1/2. A quantum computer is said to solve a problem if, for every instance, its answer will be right with high probability. If that solution runs in polynomial time, then that problem is in BQP. BQP is contained in the complexity class, or more precisely in the associated class of decision problems P number P, which is a subclass of P-space. BQP is suspected to be disjoint from NP-complete in a strict superset of P, but that is not known. Both integer factorization and discrete log are in BQP. Both of these problems are NP problems suspected to be outside BPP, and hence outside P. Both are suspected to not be NP-complete. There is a common misconception that quantum computers can solve NP-complete problems in polynomial time. That is not known to be true, and is generally suspected to be false. The capacity of a quantum computer to accelerate classical algorithms has rigid limits, upper bounds of quantum computation's complexity. The overwhelming part of classical calculations cannot be accelerated on a quantum computer. A similar fact takes place for particular computational tasks, like the search problem, for which Grover's algorithm is optimal. Bohmian mechanics is a non-local hidden variable interpretation of quantum mechanics. It has been shown that a non-local hidden variable quantum computer could implement a search of an n-item database at most in \O\sqrt3n steps. This is slightly faster than the O\sqrtn steps taken by Grover's algorithm. Neither search method will allow quantum computers to solve NP-complete problems in polynomial time. Although quantum computers may be faster than classical computers for some problem types, those described above cannot solve any problem that classical computers cannot already solve. A Turing machine can simulate these quantum computers, so such a quantum computer could never solve an undecidable problem like the halting problem. The existence of standard quantum computers does not disprove the Church-Turing thesis. It has been speculated that theories of quantum gravity, such as M-theory or loop quantum gravity, may allow even faster computers to be built. Currently, defining computation in such theories is an open problem due to the, i.e., there currently exists no obvious way to describe what it means for an observer to submit input to a computer and later receive output. Trapped ion quantum computer. A trapped ion quantum computer is one proposed approach to a large-scale quantum computer. Ions, or charged atomic particles, can be confined and suspended in free space using electromagnetic fields. Qubits are stored in stable electronic states of each ion, and quantum information can be transferred through the collective quantized motion of the ions in a shared trap, interacting through the Coulomb force. Lasers are applied to induce coupling between the qubit states, for single qubit operations, or coupling between the internal qubit states and the external motional states, for entanglement between qubits. The fundamental operations of a quantum computer have been demonstrated experimentally with the currently highest accuracy in trapped ion systems. Promising schemes in development to scale the system to arbitrarily large numbers of qubits include transporting ions to spatially distinct locations in an array of ion traps, building large entangled states via photonically connected networks of remotely entangled ion chains, and combinations of these two ideas. This makes the trapped ion quantum computer system one of the most promising architectures for a scalable, universal quantum computer. As of April 2018, the largest number of particles to be controllably entangled is 20 trapped ions. Contents. The Paul ion trap. The electrodynamic ion trap currently used in trapped ion quantum computing research was invented in the 1950s by Wolfgang Paul, who received the Nobel Prize for his work in 1989. Charged particles cannot be trapped in 3D by just electrostatic forces because of Earnshaw's theorem. Instead, an electric field oscillating at radio frequency, RF, is applied, forming a potential with the shape of a saddle spinning at the RF frequency. If the RF field has the right parameters, oscillation frequency and field strength, the charged particle becomes effectively trapped at the saddle point by a restoring force, with the motion described by a set of Matthew equations. This saddle point is the point of minimized energy magnitude, \displaystyle \overwrite x, for the ions in the potential field. The Paul trap is often described as a harmonic potential well that traps ions in two dimensions, Assume \display style \wide height x and \display style \wide height y without loss of generality, and does not trap ions in the \display style \wide height z direction. When multiple ions are at the saddle point and the system is at equilibrium, the ions are only free to move in. Therefore, the ions will repel each other and create a vertical configuration in, the simplest case being a linear strand of only a few ions. Coulomb interactions of increasing complexity will create a more intricate ion configuration if many ions are initialized in the same trap. Furthermore, the additional vibrations of the added ions greatly complicate the quantum system, which makes initialization and computation more difficult. Once trapped, the ions should be cooled such that \display style k underscore bt \bar omega underscore z, see lambdic regime. This can be achieved by a combination of Doppler cooling and resolved sideband cooling. At this very low temperature, vibrational energy in the ion trap is quantized into phonons by the energy eigenstates of the ion strand, which are called the center of mass vibrational modes. A single phonon's energy is given by the relation \display style bar omega underscore z. These quantum states occur when the trapped ions vibrate together and are completely isolated from the external environment. If the ions are not properly isolated, noise can result from ions interacting with external electromagnetic fields, which creates random movement and destroys the quantized energy states. History of trapped ion quantum computing. The first implementation scheme for a controlled knot quantum gate was proposed by Ignacio Serac and Peter Zoller in 1995, specifically for the trapped ion system. The same year, a key step in the controlled knot gate was experimentally realized at NIST Ion Storage Group, and research in quantum computing began to take off worldwide. Many traditional ion trapping research groups have made the transition to quantum computing research, while, more recently, many other new research groups have joined the effort. An enormous amount of progress in this field has been made in the past decade, and trapped ions remain a leading candidate for quantum computation. Requirements for quantum computation. The full requirements for a functional quantum computer are not entirely known, but there are many generally accepted requirements. DiVincenzo outlined several of these criterion for quantum computing. See DiVincenzo's criteria. Qubits. Any two-level quantum system can form a qubit, and there are two ways to form a qubit using the electronic states of an ion. 1.2 ground state hyperfine levels, these are called hyperfine qubits. 2. A ground state level and an excited level, these are called the optical qubits. Hyperfine qubits are extremely long-lived, decay time of the order of thousands to millions of years, and phase/frequency stable, traditionally used for atomic frequency standards. Optical qubits are also relatively long-lived, with a decay time of the order of a second, compared to the logic gate operation time, which is of the order of microseconds. The use of each type of qubit poses its own distinct challenges in the laboratory. Initialization. Ionic qubit states can be prepared in a specific qubit state using a process called optical pumping. In this process, a laser couples the ion to some excited states which eventually decay to one state which is not coupled to the laser. Once the ion reaches that state, it has no excited levels to couple to in the presence of that laser and, therefore, remains in that state. If the ion decays to one of the other states, the laser will continue to excite the ion until it decays to the state that does not interact with the laser. This initialization process is standard in many physics experiments and can be performed with extremely high fidelity, 99.9%. 0 \Wrangle, 0 phonons. Measurement. Measuring the state of the qubit stored in an ion is quite simple. Typically, a laser is applied to the ion that couples only one of the qubit states. When the ion collapses into this state during the measurement process, the laser will excite it, resulting in a photon being released when the ion decays from the excited state. After decay, the ion is continually excited by the laser and repeatedly emits photons. These photons can be collected by a photomultiplier tube, PMT, or a charge-coupled device, CCD, camera. If the ion collapses into the other qubit state, then it does not interact with the laser and no photon is emitted. By counting the number of collected photons, the state of the ion may be determined with a very high accuracy, 99.9%. Arbitrary single qubit rotation. One of the requirements of universal quantum computing is to coherently change the state of a single qubit. For example, this can transform a qubit starting out in 0 into any arbitrary superposition of 0 and 1 defined by the user. In a trapped ion system, this is often done using magnetic dipole transitions or stimulated Raman transitions for hyperfine qubits and electric quadrupole transitions for optical qubits. The term rotation alludes to the block sphere representation of a qubit pure state. Gate fidelity can be greater than 99%. The operations \displaystyle r_x, \theta, and \r_y, \theta, can be applied to individual ions by manipulating the frequency of an external electromagnetic field from and exposing the ions to the field for specific amounts of time. These controls create a Hamiltonian of the form \h_ii equals \h_bar\omega/2, s_plus \exp, I/phi, plus s_dash \exp, I/phi. Here, s_plus and \s_dash are the raising and lowering operators of spin, see ladder operator. These rotations are the universal building blocks for single qubit gates in quantum computing. To obtain the Hamiltonian for the ion-laser interaction, apply the Jaynes-Cummings model. Once the Hamiltonian is found, the formula for the unitary operation performed on the qubit can be derived using the principles of quantum time evolution. See the page Hamiltonian, Quantum Mechanics, for a discussion of time evolution and its applications with the Schrödinger equation. Although this model utilizes the rotating wave approximation, it proves to be effective for the purposes of trapped ion quantum computing. 2-qubit entangling gates. Besides the controlled NOT gate proposed by Sirac and Zoller in 1995, many equivalent, but more robust, schemes have been proposed and implemented experimentally since. Recent theoretical work by Garcia-Rapal, Sirac, and Zoller have shown that there are no fundamental limitations to the speed of entangling gates, but gates in this impulsive regime, faster than 1 microsecond, have not yet been demonstrated experimentally. The fidelity of these implementations has been greater than 99%. Scalable trap designs. Quantum computers must be capable of initializing, storing, and manipulating many qubits at once in order to solve difficult computational problems. However, as previously discussed, a finite number of qubits can be stored in each trap while still maintaining their computational abilities. It is therefore necessary to design interconnected ion traps that are capable of transferring information from one trap to another. Ions can be separated from the same interaction region to individual storage regions and brought back together without losing the quantum information stored in their internal states. Ions can also be made to turn corners at a T-junction, allowing a two-dimensional trap array design. Semiconductor fabrication techniques have also been employed to manufacture the new generation of traps, making the ion trap on a chip a reality. Such as TRAP, the quantum charge-coupled device, QCCD, has been designed by Kielpinski, Monroe, and Wineland. QCCDs resemble mazes of electrodes with designated areas for storing and manipulating qubits. The variable electric potential created by the electrodes can both trap ions in specific regions and move them through the transport channels, which negates the necessity of containing all ions in a single trap. Ions in the QCCD's memory region are isolated from any operations and therefore the information contained in their states is kept for later use. Gates, including those that entangle two ion states, are applied to qubits in the interaction region by the method already described in this article. Decoherence in scalable traps. When an ion is being transported between regions in an interconnected trap and is subjected to a non-uniform magnetic field, decoherence can occur in the form of the equation below, see Zeeman effect. This effectively changes the relative phase of the quantum state. The up and down arrows correspond to a general superposition qubit state, in this case the ground and excited states of the ion. Additional relative phases could arise from physical movements of the trap or the presence of unintended electric fields. If the user could determine the parameter alpha, accounting for this decoherence would be relatively simple, as known quantum information processes exist for correcting a relative phase. However, since alpha from the interaction with the magnetic field is path-dependent, the problem is highly complex. Considering the multiple ways that decoherence of a relative phase can be introduced in an ion trap, reimagining the ion state in a new basis that minimizes decoherence could be a way to eliminate the issue. One way to combat decoherence is to represent the quantum state in a new basis called the decoherence-free subspace, or DFS, with basis states \displaystyle \upperrow \down arrow \wrangle and \displaystyle \down arrow \upperrow \wrangle. The DFS is actually the subspace of two ion states, such that if both ions acquire the same relative phase, the total quantum state in the DFS will be unaffected. Overall analysis of DiVincenzo's criteria. Trapped ion quantum computers theoretically meet all of DiVincenzo's criteria for quantum computing, but implementation of the system can be quite difficult. The main challenges facing trapped ion quantum computing are the initialization of the ion's motional states, and the relatively brief lifetimes of the phonon states. Decoherence also proves to be challenging to eliminate, and is caused when the qubits interact with the external environment undesirably. CNOT gate implementation. The controlled NOT gate is a crucial component for quantum computing, as any quantum gate can be created by a combination of CNOT gates and single qubit rotations. It is therefore important that a trapped ion quantum computer can perform this operation by meeting the following three requirements. First, the trapped ion quantum computer must be able to perform arbitrary rotations on qubits, which are already discussed in the arbitrary single qubit rotation section. The next component of a CNOT gate is the controlled phase flip gate, or the controlled Z gate, see quantum logic gate. In a trapped ion quantum computer, the state of the center of mass phonon functions as the control qubit, and the internal atomic spin state of the ion is the working qubit. The phase of the working qubit will therefore be flipped if the phonon qubit is in the state 1/wrangle. Lastly, a swap gate must be implemented, acting on both the ion state and the phonon state. Two alternate schemes to represent the CNOT gates are presented in Chuang's Quantum Computation and Quantum Information and Sirac and Zoller's Quantum Computation with cold_trapped ions.
ZipUtateUSAcommand.com